friends, in this video we are going to solve a problem on Nyquist plot. So let's take the problem. So our problem is we have to investigate the stability of a closed loop system with the following open loop transfer function using Nyquist stability criteria. So we have to make a comment about the stability, that whether the system is stable or it is unstable using the Nyquist stability criteria, and the open loop transfer function is given to us in the question. So let's try to solve this problem. For the first step of the Nyquist stability criteria, this transfer function is given to us in the S domain. So we are going to convert it into the frequency domain. That is, we are going to replace the S by j omega. So we have replaced the S by j omega. So our transfer function has become g j omega h j omega equals to k s. In place of s we have written j omega, so j omega plus 3 upon j omega, and in multiplication we have j omega minus 1. Now we are going to take 3 as common and we are going to take this k as 1. So the transfer function will become k is equals to 1 here, and 3 has been taken as common. So 3, we have 1 plus 0.33 j omega. Okay, so here we have taken k equals to 1 and 3 has been taken as common. So we are left with 1 plus j omega by 3. So 1 by 3 is 0.33 j omega, and here we have j omega minus 1 plus j omega. Okay, so this is our transfer function in the frequency domain. Now we are going to calculate the magnitude and phase angle of this transfer function. So we have magnitude three is as it is. Then we have this as a complex number, so its magnitude will be under root of real part square plus imaginary part square. So real part is 1, its square will be 1, plus we have 0.33 omega as the imaginary part, so 0.33 omega square. Whenever we have a complex number like x plus iota y, then its magnitude is x square plus y square, and its phase angle is tan inverse of y by x, that is imaginary part upon the real part. So here we have taken the magnitude of the numerator, then denominator, this its magnitude will be omega, then under root of 1 plus omega square. Okay, now we are going to take the phase angle. So phase angle will be tan inverse of the imaginary part upon the real part. So tan inverse of 0.33 omega upon real part is 1. Then we have j omega, so we will take minus sign here. because it is the phase of the denominator part. So minus sign will be there. Minus tan inverse of omega upon 0 minus tan inverse of omega upon minus 1. Okay. Now we are going to solve this. Tan inverse of 0.33 omega. This is tan inverse of infinity. Okay, so it will be 90 degrees. Then minus, we have this as tan inverse of y upon minus x. So this is going to be written as tan inverse of y upon minus x is equal to pi minus tan inverse of y by x. So here we are going to write minus pi minus tan inverse of omega. Okay, so just simplify it. This is minus 90 minus 180 degrees, so it will be minus 270 plus tan inverse of 0.33 omega, and this is minus minus plus, so plus tan inverse of omega. So we have got the magnitude and the phase angle of the transfer function. This is the expression for magnitude and this is the expression for the phase angle. Now Nyquist plot, it is the plot of the magnitude and the phase angle with respect to frequency. Okay, so according to frequency we are going to draw it, and then we are going to, just like polar plot, we draw first the polar plot and then we take the mirror image of the polar plot. So we are going to take different values of omega, and for those different values we will calculate the magnitude. Okay, so first we will form the table for magnitude and then for the phase angle we will take different values of omega. The first value of omega we will take it as 0. So when we put value of omega as 0 in the magnitude equation here, so this will become 0, this is 0, this is 0. So the magnitude comes out to be 3 upon 0, that is infinity. So magnitude value will be infinity. Now, if we are going to put omega equals to 0 in this phase angle equation, then minus 270 plus tan inverse of 0 plus tan inverse of 0. So, tan inverse of 0 is 0 degrees. So, the phase angle will come out to be minus 270 degrees. So, we have here minus 270 degrees. Then 1, 5, 10 and infinity. We can take different values of omega. So now we will take the next value of the frequency, that is omega equals to 1. Now we are going to put this omega equals to 1 in this equation. So it will become 1 plus 0.33 square, and here we have 1 plus 1, that is root 2. So when we calculate this we will get the magnitude as 2.2. Now here we have, if we put this, then we have tan inverse of 0.33 plus tan inverse of 1. So we are going to calculate this phase angle and we will get the value as minus 206.7 degrees. Then we are going to put omega equals to 5, omega equals to 10 in these two equations for magnitude and phase angle, and we will get the values as 0.2, now when we put omega equals to infinity here in the magnitude, then we will get 3 upon infinity. So it will, the whole term will become 0. So our magnitude is 0. And here if we put tan inverse of infinity plus tan inverse of infinity, so it will become 90 plus 90, that is 180, and minus 270 plus 180 will become 90 degrees. So we will get minus 90 degrees. So for these different values of omega, we have obtained the different values of magnitude and the phase angle, and we are going to use these values to plot the polar plot. Okay, so first we will draw the polar plot using this table. Okay, so let's draw it. So now we will use that table to draw the polar plot. So here we will have, this is our imaginary axis, this is real axis, this is 0 degrees. Okay, now we will divide here we will divide the magnitude. Okay, so here we have positive magnitudes value, so this is 0. Now first we will draw the phase angle terms. Now for omega equals to 0, the phase angle is minus 270 degrees, and minus 270 degrees is here. So the plot will start from infinity because magnitude is infinity here. So here we will have, the plot will start like this. Then for omega equals to 1, we have the magnitude as 2.2 and phase angle is minus 206.7 degrees. So we will draw the line for minus 206.7 degrees. When we have the negative angle, then it will start in this clockwise direction, and if we have the positive angle, then it will goes in the anti-clockwise direction. So here we are having minus 206.7, so it will be, this is minus 180, so minus 206.7 will goes like this. This is minus 206.7 degrees. Then we have the next, for omega equals to 5, we have minus 132.5 degrees. So it is minus 180. So minus 132 will be somewhat here. Then for omega equals to 10, we have the phase angle as minus 113 degrees. So it will be somewhat here. This is for omega equals to 0. This is for omega equals to 1. This is for omega equals to 5. Omega equals to 10. Now for omega equals to infinity, the magnitude is 0, but the phase angle is minus 90 degrees. So magnitude 0 will be here and phase angle minus 90 degrees already here. So we can write omega equals to infinity here. Now just mark the points approximately for the magnitudes. For omega equals to 1, the magnitude was coming out to be 2.2. So here we have 0.4. Okay, so in this way we are going to mark all the points. Just take appropriate table, the scale on both the sides, so you can mark the points here. We are taking, suppose we are taking the 2.2 point here. Okay, so this is, we are going to meet. Okay, now for omega equals to 5, the magnitude is coming out to be 0.2. So 0.2 will be here. So this will come Then for omega equals to 10, the magnitude is coming out to be 0.1. So it will be here. And for omega equals to infinity, the magnitude is 0. So the polar plot, it is starting from the omega equals to 0 and it is terminating at omega equals to infinity. So we will draw the arrows here. So this is the polar plot of the system. Now we have to draw the Nyquist plot, and Nyquist plot is the mirror image of the polar plot. So we will draw the mirror image here. So we have drawn the mirror image and we have joined all the points. So this is the Nyquist plot of the system. Now to check the stability of the system using the Nyquist plot, we have to see that how many points, how many times this Nyquist plot is encircling the point -1 plus J0. Okay, so we have, if we can see here, this is encircling for one time. Okay, the encirclements in the anti-clockwise direction, see it is going here, -1 will be somewhat here, okay, between 0.8 and 1.2, and it is encircling it, one encirclement is there. So the encirclements, that is n equals to +1. Okay, now here we have assumed, when we have started the numerical, we have assumed that k is equal to 1. That is the gain. So when we are increasing the value of this gain k, then this encirclement will goes to this side. Okay. So as the k is increased, the -1 plus j0 point will move inside the loop. Okay. So for checking the stability, P is equal to 1 because number of poles which are lying on the right half of the S plane, it is 1. So P is equals to 1 and N is also equals to +1. So Z is equals to P minus N, that is 1 minus 1 is 0. So we can say that Z is equals to 0 but P is equal to 1. So the system is open loop unstable, but system is closed loop stable. So we have made the comment about the stability of the system by checking the value of P and Z. P is coming out to be 1 and Z is equals to 0. So we can say that the system is open loop unstable, but it is closed loop stable. So in this way, using the Nyquist plot, we can make a comment about the stability of the system. What we have to do first, we will convert we will obtain the transfer function in the frequency domain, that is Gj omega and Hj omega. Then we will calculate the magnitude and phase angles of the transfer function, and for different values of omega we will calculate the value of the magnitude and the phase angle. Then we are going to draw the polar plot, that is the plot of the magnitude and the phase angle. Okay, then the Nyquist plot, it is the mirror image of the polar plot. So from that we will see that how many encirclements are there of the -1 plus j0 point, and according to that we are going to check the value of P and Z, and then we can make a comment about the stability of the system. So I hope that this problem is clear to you. Thank you.